At the University of Illinois, researchers have developed a technology that has many applications in the fields of biotechnology and engineering. The tunable nanopore technology begins with a semiconductor wafer with many nanopores. The wafer and nanopores are made with conventional semiconductor processing, technology utilized on a large scale today. This technology can be applied to filter body fluids, to selectively filter urea or creatinine, or to read strands of DNA. The nanopore can also trap more complex entities such as an amino acid. The geometric elements of the nanopore, such as the membrane thickness, approach angle, and diameter, as well as the semiconductor material and doping, can be adjusted to fit the user's specific need. The flexibility of the technology allows for a higher functionality. Changing certain elements of the nanopore allows for ions, species with charge, or DNA strands to selectively pass through the wafer. For example, we can selectively filter calcium 2+ from sodium 1+ while trapping chloride ions. The filtering process begins by creating a charged membrane, resulting in a field that spans the length of the nanopore. Entities with a net charge will migrate through the pore's field toward the corresponding opposite charge. Alternatively, the electrical conditions of the membrane can be changed to create a stronger field gradient in the membrane pore. For instance, a single membrane and pore immersed in ionic fluid and bracketed by charge plates. Adding a bias to the membrane creates a charged membrane and field within the pore. The electrical conditions of the membrane can be changed to trap entities within the pore. The stronger the bias, the stronger the field gradient in the membrane pore. To review, a membrane and pore immersed in ionic fluid and bracketed by charge plates cause a field within the pore. This field causes entities within the pore to migrate to the corresponding charge. A manipulation in membrane bias creates a change in the field gradient in the membrane pore. So far, the demonstrations have illustrated the technology operating with direct current. However, one very important aspect of this technology is that it can operate with alternating current. This transition to adjustable alternating current character is very useful for trapping or selectively filtering complex entities. Remember that the physical cross-section you see here is adjustable in many ways. In this view, we see an environment containing several ions. When a bias is applied, these ions drift predictably towards the plate with opposite bias. To enhance flexibility, we now introduce a bias to the membrane. This bias creates charge in the membrane and a resulting charge field in the membrane pore. With the addition of charge to the membrane, the movement of the ions depends upon more than the charge of the ions. Their size becomes a factor as well. This enhanced flexibility is a tremendous improvement in designing specialized pores. This added design latitude was conceived by the Illinois team. Modeled here, this enhancement allows creation of parameters to control the migration of specific entities through the pore. In this way, the properties of the membrane can be changed to trap specific entities within the pore. As is shown here, the chloride ion becomes trapped in the pore and is separated from the calcium 2+ and sodium 1+. Once an entity is trapped within the pore, it is possible to measure the impedance of the pore to understand what nanoentity has been trapped without interference from other elements. Furthermore, we can create multiple areas of different charges on the membrane. This additional parameter can be used to trap specific entities with known net charge zones. In this case, we have trapped a simple amino acid in the pore. Finally, with the correct arrangement of pore geometry, plate potential, and correct membrane charge bias, it will be possible to pull a strand of DNA through the diameter of the pore, effectively straightening out the strand. This change in structure will cause only 1/2 of a base pair to enter the effective pore. A manipulation of field, combined with the straightening of the DNA, allows impedance changes in the pore, corresponding with each half of each base pair to be measured. For more information on partnering with the University of Illinois on this exciting technology, please contact the Office of Technology Management at 217-333-7862. This technology is the primary substance of several patent applications. This video was created by the staff at the Visualization Lab at the Beckman Institute for Advanced Science and Technology at the University of Illinois at Urbana-Champaign.